right, lesson 13 is exponential and logarithmic equations and inequalities. And so here, our skills and learning objectives are going to be use the properties of exponents and logarithms to solve equations and inequalities. We're going to solve, when solving exponential and logarithmic equations, we're going to analyze for extraneous solutions. And we're going to use inverse operations to write exponential and logarithmic equations that reverse the mapping. All right, so it says let's consider the following equation: 2 to the x equals 64 and log of 3x equals log of x minus 8. We can use the one-to-one properties below to solve equations algebraically, but how do we handle the more difficult equations and inequalities? All right, so they start out with the one-to-one properties, which we've already talked about. Just says that basically, if I'm looking at the exponential form on the left there, that if I can get like bases, then I can ignore the base and set the exponents equal and solve. And then the same thing on the right there with the log functions. If I can get log base b of something, it equals log base b of something else. As long as log bases are the same, then I can ignore them, and I know what I'm taking the logs of have to be equal. So I could say, in this case, u equals v, and solve for whichever variable I needed to. And so we're going to see that when we do example 1 coming up here. Remember, in exponential equations, equation in the form of y equals b raised to some cx, where the exponent includes a variable, and a logarithmic equation is an equation that includes a logarithm involving a variable. So just remember that exponential has x in the exponent, where a logarithmic equation has log not in the exponent. Oh, I'm sorry, I skipped example 1 here. I thought that was the next example. So going back, let's look at example 1. So it has 2 to the x minus 5 equals 64. Well, we know that 64 has a base of 2. It's 2 to the 6. And so we have 2 to the x minus 5 equals 2 to the 6. Since my bases are equal, I can ignore them. And I know that means the exponents has to be equal. So x minus 5 has to equal 6. Add the 5. And we find that x equals 11. Now we can do the same thing on example 1b there with logarithms, but now be careful because it can only be a log equals a log, not 1/2 log equals 2 log, not 2 log equals 2 log even, okay? So you have to get rid of these numbers in front. So remember, the coefficient can be rewritten as the exponent. So this is the same as log of x to the 1/2 equals log of 2 squared. Now my logs have the same base, so I can ignore them. X to the 1/2, remember, that's the same thing as the square root of x, equals, and 2 squared is 4, and then I can solve for x. And so I get x equals 16. Now, something we haven't had to do because we haven't solved log equations, per se, is when you solve for x here, you have to check your answer. Because remember, when you take the log of a number, that number has to be greater than 0. So like right here where I have an x, I need to check this answer, that 16, and make sure, can I take log of 16? As long as what I'm taking the log of is greater than 0, then it's okay. And if I just plug in the 16 there, it's good, so 16 is our answer. It doesn't mean that our x value can't be negative. It just means that when I plug it back into the log equation there that I have circled, I have to have a positive answer there, okay? So, like what I'm saying, if I had log of x plus 4, let's say, equals something else, and I solve and I get x equals -2. But when I plug this back in up here, -2 plus 4 is 2, so I'm really just taking log of 2, which would be okay, which means the -2 could be my answer. So it doesn't mean our x can't be negative, just when we check it, when we plug it back in, we have to get a positive answer. All right. Then to example 2. So notice on this one, my exponential part's not by itself. I have that 24 in front. So we're going to move the 24 over first. And so we get 1/2 to the x over 3 equals 1/4. Now, if you're okay with fractions, you can go ahead and get your, you can say, well, 1/4 is 1/2 to the, well, 1 to the anything is 1, but 2 to the what gives me 4. It would be squared. If you're not okay with fractions, you can go to negative exponents and use it. All right, so I've got 1/2 to the x over 3 equals 1/2 to the second. Bases are the same, so ignore them. So that means x over 3 has to equal 2, and then just solve for x. And so we get x equals 6. This one was an exponential function. I don't have to check my answer. That is my answer. I mean, I should to make sure I got it right, but I don't have to. All right, example 3. So we've got 2 log base 3 of x equals 3 log base 3 of 4. Remember, we can't have these coefficients in front, so let's move them as the exponents. So we get log base 3 of x squared equals log base 3 of 4 cubed. Log base 3's are the same, so we can ignore them. So we know that means that x squared has to equal 4 cubed is 64. And then we're going to take the square root. And so we get x equals plus or minus 8. So we got x equals -8, and we got x equals +8. Now, because we have log at the very beginning, I've got to go check these. So let me check that -8. So when I plug -8 in right here, what is log base 3 and -8? Can I take the log of -8? I cannot, which means this is what they call an extraneous solution. Which means it worked for our problem, like it worked when we worked it out. It's not incorrect. It just doesn't work for our original problem, okay? And then you got to check the 8. So when I plug in this +8 right here, log base 3 of 8, I can take that. It's positive. So 8 is the only answer we get there. All right, applying the definition of a log property. It says we can use the definition of a logarithm to rewrite exponential equations in order to solve. When solving logarithmic equations, be sure to determine the domain of the variable first to avoid extraneous solutions. So again, just check your answers at the end. Make sure that it's okay for that answer will work when you plug it back into any of the log functions you have that has an x in it. So, for example, 4. Here I notice I have log base 2 of 4x equals 5. There's no logs to combine. I have a single logarithm on one side, so I'm going to change it to exponential. And so just a kind of a recap, remember you have log base b of x equals y, and that can be rewritten as b to the y equals x. So in this case, my base is 2. My x is the 4x, and my y is 5. So when I go to b to the y equals x, so 32 equals 4x, divide by 4, and we get x equals 8. Now make sure you check it. So when I come back up here to the problem, when I plug in 8, 4 times 8 is 32. That's a positive number, so 8 is my answer. It works. Example 5, this time I have 2 logs on the left there. So I can combine those logs, and because they're being added, I can combine them with multiplication. So I'm going to take log of x times x plus 15 equals 2. And then I can go ahead and distribute the x, so log of x squared plus 15x equals 2. And now this is like example 4, I've got that single logarithm on one side. So let's change it to exponential. So my base is 10, my x is x squared plus 15x, and my y is 2. So b to the y equals x. So 100 equals x squared plus 15x. So remember, when you have an x squared and an x, you're going to have to factor, which means I need this set equal to 0. So I'm going to move the 100 over. And so it's 3 terms, so this is just our x box. So we're going to multiply to negative 100, combine to positive 15, which is 20 and negative 5. So we get x plus 20, x minus 5, and it's equal to 0. So then set each factor equal to 0 and solve. So we get x equals negative 20, and we get x equals 5. Don't forget, you had a log at the very beginning, so make sure you check your answer. So I'm going to check the negative 20 first. When I come up here to the first one, log of negative 20, I can't take it, so negative 20 doesn't work. check the 5. When I plug in the first one, log of 5, that's good. The second log there is log of 5 plus 15. 5 plus 15 is 20. I can take log of 20, so it's good. So 5 is my only solution. All right, example 6. Now, I can't get like bases on example 6. 26 doesn't have a base of 8, and 8 and 26 don't have a same base. So because of that, I'm going to take a log. Now, there's different ways to do this. You could just go from your MB to the y equals x. So you could just change it to log base b of x equals y, which is going to be probably our easiest. So I'm going to take, I know that my b is 8, my y is the x minus 3, and my x is the 26. So I'm going to take log base b of my x equals y. And then you're just solving for your variables. So add the 3. And so we get log base 8 of 26 plus 3 equals x. It is not log base 8 of 29, guys. We're just taking the log base 8 of 26, getting an answer, and then we're going to add 3 to it. So you can write it like that, or if you need to, put the 26 in parentheses. Because remember, if you hit log on your calculator, it's going to open a parenthesis, and after the 26, you would need to close it. All right, so that's my exact answer is log base 8 of 26 plus 3. And I could type that in my calculator, and my decimal approximation would be 4.567. All right, now example 7 is really just kind of weird. We've got e to the x equals pi raised to the 1 plus x. So we could do the same thing we did here, but it's like, which one do we get rid of? Which one do we prefer to have as a base? So I would prefer to have my e, because I know there's something special when there's base e. All right, so I'm going to let my base be e. My x is x, I'm sorry, it's b to the y, so my y is the x, and my x is that whole other side. So we get log base b of x equals y. Now we know that log base c is the same as the natural log. And I still have the issue with I have two x's here. But remember, we have that rule that says this exponent can be moved in front as the coefficient. Now that exponent is together, so keep it together. Which means I need to distribute this natural log of x. I'm sorry, this should be natural log of pi. I apologize. So I got 1 times the natural log of pi plus x times the natural log of pi equals x. Now, I'm trying to solve for x, so I need to get my x's on the same side. So I'm just going to move this one over. It's with the natural log of pi, so move it as a term. So I got the natural log of pi equals x minus x natural log of pi. And then because on this right side here, they have an x in common, let's common factor it out. Leave the left side alone, and then solve for x by dividing by 1 minus natural log of pi. So we get x equals natural log of pi over 1 minus natural log of pi, which has a decimal approximation of negative 7.909. Now notice on both of these problems, on 6 and 7, I didn't check my answer. But my original equation did not have a log in it, okay? So I should check it to see, will I get the same answer on both sides? But I don't have to check it. I don't have to worry about those extraneous solutions going on. All right, then example 8. We're going to solve by graphing 2 to the 3x equals 9. So we've done something similar to this before. If you have two things set equal, remember you can put the left side in y1, the right side in y2, and then you're just going to adjust your window so you can see the intersection and find it. All right, so you're going to, in our y1, we would type in 2 to the 3x. In our y2, we're going to type in 9. On our regular window, we should be able to see that intersection already, so I shouldn't have to adjust my window, but you can if you need to. And so then we're just going to go to second, trace, which is that calc button. Number 5 says intersect, and hit enter, enter, enter. And when you do, it's going to tell you that the x value is 1.057 approximately. And then we could do the same thing with the table, okay? So we could go to our table and look, and you want to find the one that's closest to 9, and so you could go to your table. If you go to second window, that'll give you your table startup, because our tables are by whole numbers, and we want it to, well, they're showing 2 decimal places, but 2 or 3 decimal places, okay? Do your table start at 1, and then your change in the table is how do you want to see those x's? Do you want to see 1.1, 1.2, 1.3, 1.4? In that case, you would do a change in the table of 0.1. If you want to see 1.01, 1.02, 1.03, you do a change in the table of 0.01. Bigger than that, I would be really careful because, or smaller than that, because it's going to take you forever to go through them. So if nothing else, kind of narrow it down, and then you can change your table start. So like on this one, if I wanted 3 decimal places, I wouldn't just jump to 0.001 yet. Okay, so I would go through and I do my change in table like they said here, and I look and I can see that it's somewhere between those two will give me the y value of 9. So I know it's between 1.05 and 1.06. Now if I wanted to get to that third decimal place, then what I would do is I'd go back here and change my table start to that 1.05 and change my change in the table to 0.001. And then when I go in and look at my table, that's going to give it even closer, and so that I can estimate a better answer. And I would just pick whichever one was closest to the 9. All right, so that's how you can tell it by your table. All right, and that is the end of lesson 13A.